Let's go back to the 1920s. Physics was in crisis. The neat clockwork universe of Newton, where everything moved in predictable paths, was breaking down at the atomic level. Electrons weren't behaving like tiny planets orbiting a sun. They were acting weird. Sometimes they were particles, tiny points in space. Other times, they were waves, spread out and ethereal. It was chaos. It was madness. And then, in 1926, an Austrian physicist named Erwin Schrödinger wrote down an equation. It wasn't just a string of symbols. It was a revelation. Schrödinger's equation didn't tell you where an electron is. Instead, it described a wave function, a cloud of probabilities, a map of every possible place that electron could be. It suggested that until you look, the electron is in all those places at once, a shimmering ghost of potential. The moment you observe it, that cloud of possibility collapses into a single definite point. This is the equation that explains why the atoms in your body don't fly apart, how the sun fuses hydrogen into helium to create the light and heat that sustains us, and how the semiconductors in the device you're watching this on are even possible. Think about it like this. Imagine you release a single drop of ink into a glass of water. Classical physics would try to track the path of that single drop. Schrödinger's equation, on the other hand, describes how the entire cloud of ink diffuses, predicting the probability of finding an ink particle anywhere in that water. It's the rulebook for the universe's magic show, the blueprint that guides the quantum dance. It's not just an equation. It's a new philosophy for existence, one built on probability, not certainty. So how did we go from a philosophical blueprint to a technological revolution? It started with a radical thought. Fast forward to 1980. The digital age was dawning. Computers were getting faster, powered by bits, the simple, reliable language of O south and 1 south, on or off. They were masters of logic. But a physicist named Paul Benioff looked at these machines and saw a fundamental disconnect. Our computers spoke a language of certainty, but the universe, at its core, spoke the language of quantum probability. He asked a question that would change everything. What if we built a computer that mirrored the quantum world itself? This was the birth of the quantum Turing machine, a theoretical device that wasn't built on bits, but on qubits. A bit is like a light switch. It's either on or off. A qubit is more like a spinning coin. While it's in the air, it's not heads or tails. It's a blend of both possibilities. This state is called superposition. A qubit can be a 0, a 1, or both at the same time. This simple difference unlocks an exponential power. 2 bits can only be in one of 4 states, 0, 1, 10, or 11. But 2 qubits in superposition can represent all 4 of those states simultaneously. This idea was so profound that it captured the imaginations of 2 of the era's greatest minds, Yuri Manin and Richard Feynman. They realized that if you want to simulate a quantum system, like a complex molecule for a new drug or a new material for a solar panel, a classical computer would choke. It's like trying to describe a symphony by playing one note at a time. It's hopelessly inefficient. Feynman famously declared, "Nature isn't classical. Damn it. And if you want to make a simulation of nature, you better make it quantum mechanical." They envisioned a machine that didn't just calculate. It would embody the quantum chaos it was trying to understand. Have you ever considered that to truly solve the universe's greatest puzzles, we might need to build a piece of the universe itself? While some physicists dreamed of building quantum computers, others saw a more immediate application for these bizarre quantum rules, creating secrets that could never be broken. In 1984, Charles Bennett and Gilles Brassard unveiled a system called quantum key distribution, or QKD. It's a method for creating a secret key that's not just hard to crack, but physically impossible to crack without being detected. Let's make this real. Imagine 2 people, let's call them Alice and Bob, who are spies needing to share a secret plan. The enemy, Eve, is a master hacker who can intercept any message they send. With classical encryption, Eve could copy the message, work on cracking it later, and Alice and Bob would never know. But with QKD, the game changes. Alice sends her secret key to Bob, encoded in the quantum states of individual photons, particles of light. Here's the genius part. Rooted in the observer effect we talked about with Schrödinger's equation, the very act of observing a quantum system changes it. If Eve intercepts a photon to read its state, her measurement collapses its wave function, altering it in a tiny but detectable way. It's like a spy trying to read a letter written on a fragile piece of parchment. Their fingerprints will inevitably smudge the ink. After Alice sends her stream of photons, she and Bob get on a public channel of regular phone call and compare a random sample of what she sent and what he received. If every photon Bob received matches what Alice sent, they know the line is secure. The key is safe. If there are discrepancies, they know Eve is listening. The lock has screamed. They throw away the key and start over. This isn't just a clever algorithm. It's a security system guaranteed by the fundamental laws of physics. Today, this technology is already being used to protect financial institutions, government communications, and critical infrastructure. In an age where digital privacy feels like a losing battle, could a law of the universe be our final unbreakable shield? To truly appreciate the quantum leap, we need to understand the world we live in now. Classical computers are the tireless workhorses of our civilization. They are magnificent machines of logic, processing information in a straight, linear fashion. Think of a classical computer trying to solve a complex problem as a diligent librarian in the world's largest library, tasked with finding a single piece of information. The librarian starts at the first book on the first shelf, checks it, and moves to the next, then the next, and the next. They might be incredibly fast, but they are fundamentally limited to checking one book at a time. For most things we do, sending an email, writing a document, watching this video, this is more than enough. Now imagine a quantum computer. It's not a single librarian. It's a librarian who can exist in a superposition of being in every aisle, at every bookshelf, reading every single book, all at the same time. This is the power of qubits. Thanks to superposition, they can hold multiple values at once. And thanks to another spooky quantum property called entanglement, what Einstein called spooky action at a distance, qubits can be linked. The state of one instantly influences the state of another, no matter how far apart they are. This allows them to work together in a vast, interconnected web, exploring a colossal number of possibilities in parallel. Let's use the simple example from the article, cracking the 4-digit PIN. A classical computer is a brute force attacker. It tries 000. Nope. 0001. Nope. 0002. Nope. It will methodically work its way through all 10,000 combinations. A quantum computer, leveraging superposition, would essentially test all 10,000 combinations in a single operation. It's not just faster. It's a fundamentally different way of computing. It doesn't follow a single path to a solution. It explores all paths at once. But is this quantum advantage a silver bullet for all our problems? The true power of quantum computing, its quantum advantage, lies in tackling a specific class of problems so complex that they are effectively impossible for classical computers. These are often called NP-hard problems, where the number of possible solutions explodes exponentially as the problem gets bigger. The most famous and feared example is cryptography. The security that protects your credit card information, your bank account, and your private messages is based on RSA encryption. Its strength comes from a simple fact. It's easy to multiply two large prime numbers together, but it's astronomically difficult to take that resulting large number and figure out the original two primes. A classical supercomputer might take longer than the age of the universe to crack a standard 2040 8-bit RSA key. But in 1994, a mathematician named Peter Shor developed an algorithm for a quantum computer that could do it in a matter of hours, or perhaps minutes. This isn't just a threat. It's a ticking time bomb at the foundation of our digital world. But the power isn't just destructive. It's profoundly creative. Consider logistics. A company like UPS or Amazon has to calculate the most efficient routes for hundreds of thousands of vehicles every day. The number of possible routes is staggering, a classic NP-hard problem. A classical computer can find a good enough solution. A quantum computer could evaluate all routes simultaneously to find the absolute best solution, saving billions of dollars in fuel and revolutionizing global supply chains. In medicine, designing a new drug involves simulating how a complex molecule will interact with proteins in the human body. Simulating even a relatively simple molecule like caffeine is a massive undertaking for a supercomputer. With just a few hundred stable qubits, a quantum computer could simulate molecules of incredible complexity, dramatically accelerating the discovery of new life-saving medicines. The article mentions that 300 qubits can represent more states than there are atoms in the known universe. Let that sink in. We are talking about building a machine with access to a computational space that is literally bigger than our physical reality. So what's holding us back? For all their mind-bending potential, quantum computers are not about to replace your smartphone. They are not universal problem solvers. In fact, for most everyday tasks, your laptop is vastly superior. A quantum computer trying to browse the internet would be like using a nuclear-powered submarine to go fishing in a pond. It's the wrong tool for the job. They are specialized instruments designed for problems with inherent quantum complexity. The biggest hurdle is their incredible fragility. Qubits are the divas of the computing world. Their delicate quantum state, the superposition that gives them their power, can be destroyed by the slightest disturbance, a tiny change in temperature, a stray magnetic field, even a single photon bouncing off them. This phenomenon is called decoherence, and it's the mortal enemy of quantum computing. To combat this, quantum computers are housed in some of the most extreme environments on Earth. They are kept in dilution refrigerators, multi-layered chambers that look like golden chandeliers, cooled to temperatures just fractions of a degree above absolute zero, colder than deep space. They are shielded from vibrations, radiation, and all external noise, creating a silent, frozen sanctuary where the quantum dance can play out undisturbed. Even then, errors are inevitable. Decoherence can cause a qubit to flip from a 1 to a 0, corrupting the entire calculation. The solution is quantum error correction, but it comes at a steep price. To create a single robust logical qubit that is protected from errors, you might need hundreds or even thousands of fragile physical qubits working together as a backup system. This means a problem that theoretically requires 1,000 perfect qubits to solve might need a machine with 1,000,000 physical qubits to run reliably. Building a fault-tolerant quantum computer is one of the greatest engineering challenges humanity has ever faced. Despite these challenges, the race is on. We are currently in what's called the noisy intermediate scale quantum, NISQ era. We have machines from companies like Google, IBM, and Rigetti with dozens, or even over 100 qubits. They are noisy because they are prone to errors and can only run simple algorithms for short periods before decoherence sets in. But these prototypes are already achieving incredible feats. Google's Sycamore processor made headlines by solving a specific esoteric problem in minutes that, they calculated, would take the world's most powerful supercomputer, Summit 10,000 years to complete. This milestone, dubbed quantum supremacy, was a proof of concept, a demonstration that these machines could, in fact, outperform any classical computer on its home turf. Yet, just as the quantum narrative was solidifying, a plot twist emerged from an unexpected direction: artificial intelligence. For years, scientists believed that certain complex problems, like predicting how a protein will fold into its 3D shape, a problem critical for understanding diseases, would require a quantum computer. Then, in 2020, DeepMind, an AI company, unveiled AlphaFold, An AI system that solved the protein folding problem with breathtaking accuracy using classical hardware. AI was suddenly solving problems we thought were reserved for the quantum realm. Did this mean quantum computing was becoming obsolete before it even got started? Or was something more interesting happening? The headlines might frame it as a rivalry, but the reality is far more exciting. Quantum and AI are not competitors. They are partners in discovery. They are two different keys for two different kinds of locks. AI, particularly machine learning, excels at finding patterns in massive datasets. It learns from experience. Quantum computing excels at calculating possibilities within a complex system from first principles. It calculates from the ground up. Imagine their synergy. An AI could sift through millions of chemical compounds to identify promising candidates for a new drug. Then a quantum computer could take those top candidates and perfectly simulate their molecular interactions within the body to determine their effectiveness and side effects. AI propose, quantum disposes. This partnership could slash the time and cost of developing new medicines from a decade to mere months. This collaboration is already bearing fruit in fundamental science. The article mentions the 2022 experiment, where scientists used Google's Sycamore processor to simulate a wormhole. They didn't create a real tunnel through space-time, of course. They created a holographic wormhole, a quantum simulation, where the bizarre properties of entanglement and quantum teleportation mimic the theoretical physics of a wormhole, bridging the gap between quantum mechanics and Einstein's theory of general relativity. An AI could then analyze the terabytes of data from such an experiment, searching for patterns that might lead to a unified theory of everything. The question isn't who will win. It's what wonders will they achieve together? This leads us to the most mind-bending idea of all, proposed by MIT physicist Seth Lloyd. What if the universe itself is a quantum computer? Think about it. Every time two particles interact, every time a star is born, every time a chemical reaction occurs, information is being processed. The universe, Lloyd argues, isn't just a collection of stuff. It's an ongoing cosmic-scale quantum computation. It continuously explores every possible state, every potential outcome through a universal wave function. Our reality is simply the result of that computation, collapsing the beam by observation. From this perspective, a quantum computer isn't an artificial invention. It's a small, controllable piece of the universe that we've harnessed to perform computations in the same way the universe does. The Sycamore wormhole experiment wasn't just a clever simulation. It was a moment where we used a man-made machine to speak the universe's native language, to model its own fundamental processes. If we can simulate a wormhole today, what could we simulate tomorrow? The inside of a black hole? The conditions of the Big Bang? We could be on the verge of creating tools that allow us to ask questions directly to the cosmos and get an answer back. What other secrets is the universe just waiting for us to ask about? Let's bring this back to Earth for a moment. Take a coin. Flip it. Heads or tails. Simple. Now, as the article brilliantly points out, imagine flipping it 266 times and writing down the sequence of results. The number of possible outcomes is 2 to the power of 266. That's a number with 80 digits. It is a number so vast it exceeds the estimated number of atoms in the entire observable universe. This simple experiment is a profound lesson in complexity. Our brains and the classical computers we built in our image are evolved to find simple patterns and create linear narratives to make sense of the world. We crave simplicity because the true underlying complexity of reality is overwhelming. Real-world systems, the economy, the climate, human biology, a quantum particle, are not simple. They are a chaotic dance of countless interconnected variables. Quantum computers don't get rid of this complexity. They embrace it. They are designed to navigate these impossibly vast spaces of possibility. They remind us that the most interesting problems are often the messiest. This dance between our need for simplicity and the universe's inherent complexity is what drives all science, all art, and all human progress. How do you find the simple, actionable patterns in the overwhelming complexity of your own life? The journey from Schrödinger's strange equation to the dawn of quantum computing is more than a story about technology. It's a story about a fundamental shift in how we see the world. It taught us that reality is not a fixed deterministic machine, but a shimmering ocean of probabilities. It showed us that at the deepest level, the universe is built on uncertainty, potential, and the power of observation. So, what can we take away from this for our own lives? Embrace the unknown. Life, like a quantum particle, is not a set path. It is a wave of possibilities that collapses into a single reality with every choice you make, every action you take. Don't be intimidated by complexity, whether it's a daunting project at work, a challenging personal goal, or a difficult conversation. The universe itself is a masterclass in handling complexity. Like a quantum algorithm, you can learn to approach your challenges by not just looking for a single linear path forward. Break the problem down. Explore the different possibilities, even the ones that seem unlikely. And then, most importantly, take a step. Make an observation. Collapse the wave of potential into a real outcome. Learn from it, and then face the next wave of possibilities. The universe doesn't give us simple answers, but it gives us a vast, complex, and beautiful space to ask truly big questions. So, I'll leave you with a challenge. What is your big, complex, seemingly impossible problem? What's the one thing that feels like it has more variables than atoms in the universe? I challenge you to think about it not as an obstacle, but as a space of possibility. Break it down, explore the potential paths, and take one small step forward today. You don't need a multi-million-dollar quantum computer to start building your future, just a dose of courage and a universe of curiosity. Wishing you good health and endless curiosity. If this journey into the quantum realm sparked your imagination, please subscribe to our channel for more explorations into the science and technology that are shaping our world. Let's keep asking big questions together.